Hello, everyone. Good afternoon, good evening, good morning, whatever time it may be in Vietnam, in other countries, from where you are watching this lecture on emerging digital techniques for building surveying. My name is Henry Abanda. I am an associate professor in construction IT and also a chartered engineer with the Institution of Engineering and Technology here in the UK. I'm a fellow of the UK Advanced Higher Education Academy, and my research and teaching interests are in construction IT with focus on building information modeling. I'm based at Oxford Brookes University in the United Kingdom. I will say a bit more about the project. This is part of a non-profit educational project in the development of free online educational hub being undertaken by the Institution of Investment and Construction Management at Hanoi University of Civil Engineering in Vietnam, together with the Department of Engineering at Manchester Metropolitan University. The project is supported by the Royal Academy of Engineering in the United Kingdom. The overall goal of the project is to reduce the digital skills gap in the Southeast Asian construction industry through an open access e-learning platform. You can see the logo of all the stakeholders below. At the end of this presentation, it would be great if learners can be able to appraise the challenges associated with the surveying of buildings or properties. Secondly, learners should be able to differentiate between conventional and modern surveying techniques. And lastly, learners should be able to identify the applications of modern surveying equipment. Now, I've divided this presentation into two parts. The first part is a theory part. And of course, given the context, today I can't be saying anything about digital technology without really us getting our hands dirty at some point. So the second part will actually focus on a demonstration in practice. Now, building surveying, what is it? It is a means of providing detailed evaluation of a property's condition and involve an extensive inspection. In fact, when I use the word property, you could also say buildings, and to be more general, it could be a project. So it's a means of providing a detailed evaluation of the condition of the property through an extensive inspection. And condition there is actually talking about the state of the project or the state of a property or a building. So I would say building survey is equal to condition survey. So the keywords are assessing and recording the details about a part or whole of a property or building. Now, the most common aims of building surveying might include documenting the present condition of the property, highlighting areas of failure or concern. In fact, when we are evaluating a property or a building, one of the aims is to be able to assess the present condition with the ultimate goal of identifying failures or concerns or defects, identifying the causes of past or ongoing deterioration, identifying issues that need attention to prevent serious damage. There are times that if there is a defect on a property, if you don't take an immediate action, if you don't evaluate the property to identify the main issue, it might escalate from a minor to a major damage. Identifying things that need further inquiries to preempt problems in the future, presenting conservation and maintenance recommendations, and providing estimate of the cost of any works that may be required. The most common issues identified by condition surveys include defects, any structural movement through subsidence and settlement, deterioration due to rising damp, penetrating damp, surface interstitial condensation, rot infestations such as woodworm. I won't spend time reading all of those. Some of those stuff are obvious, and you can read them at your own time. Now, typical surveying activities. Remember, we did say in one of the earlier slides that it involves intensive inspection. So the kind of activities that is involved in surveying are visual examination as opposed to invasive one, where things like carpets or floors or underfloor spacings, furniture may need to be moved or taken up. So visual examination. External examination from ground level of roofs, okay, chimneys and other surfaces. The key word there is actually external examination. Now, in the third point, depending on safety and accessibility of the different parts of the property or building, an internal examination can also be conducted, especially in the roof area. Now, those are the activities. How do we carry out these activities? We do that either using what I would say traditional or manual surveying techniques, or semi-automated surveying techniques, or advanced automated surveying techniques. We're going to see the differences between these main three methods or techniques of surveying. Now, I've said traditional stroke manual or manual surveying. And this type of surveying, we literally use our eyes and then we go around the building or property. Okay, we might use things like a tape, okay, to do some measurements, okay, and to identify defects. So that's a typical defect there on that roof, where we may see it visually, okay, and go around the building. And that's me there some 20 years ago, surveying a building, literally walking from one room to the other, and then using photographs together with that side guy, using a tape. And you can imagine how long it may take to be able to complete a building or inspecting a building, identify potential defects. Now, with a semi-automated surveying, you may have you may involve the use of equipment a bit much advanced than just using the manual tape and other minor equipment. So photographs which may subsequently be annotated may be taken using a camera. You may also be using a dictaphone, a damp meter, binoculars, torch, and a short ladder. So there's some semi-automated, there's greater involvement of use of equipment. And of course, if you think about the manual or the traditional, together with semi-automated, the disadvantages or the weaknesses is that it is error-prone, it is time-consuming, it is costly. And of course, you also have impacts, negative impacts from the weather, having to go around and having to spend too much time on site, where you can be affected, or someone surveying a building can be affected by negative weather impacts. Things like rain may hinder the smooth running or inspection process. Also safety. Imagine yourself in a room or roof. Okay? Some locations are unsafe to work in or inaccessible. And of course, when you get this kind of data through manual inspection or semi-automated techniques, it is usually very difficult to integrate that with other digital systems. I would like you to take note of that last point, limited integration capability with other systems. So you collect your data manually, it will be very, very difficult for you to be able to integrate that with other systems to be able to exploit or use the data more efficiently. And then with the advanced or automated or modern surveying techniques, we have things like the GNSS, as a global navigation satellite system, robots, drones, and 3D laser scanners. Okay, our focus will be on 3D laser scanners, although we're going to be able to say something a bit about robots and drones. So far we've covered the three major techniques of surveying buildings. Now, let's now focus on 3D laser scanning, which is a modern technique used to accurately represent physical objects. And I like that definition. It is a non-contact, non-destructive technology that digitally captures the shape of physical objects using a line of a laser. 3D laser scanners create point clouds, okay, of data from the surface of an object. In other words, 3D laser scanning is a way to capture a physical object, exact size and shape, into a computer world as a digital three-dimensional representation. Now, the different types of 3D laser scanners can be classified into terrestrial laser scanners. And you can see some examples of terrestrial laser scanners there: Leica, Trimble, Faro, Topcon, Z+F. Now, what should be noted with all those from the word terrestrial is the fact that you need a stand, okay, to be able to, you need a stand to accommodate these scanners, and that stand should be located on the earth surface, on the ground, okay, what I would call technically a tripod, okay. Then we also have handheld laser scanners, the one just like you've seen there. You use it, you hold it with the hand instead of using a tripod. Then we have wearable scanners that you wear on your body, then you move around, scanning whatever object or environment in which you find yourself or you want to do. Then you also have mobile laser scanners. Take note of the word mobile here. It's a bit confusing with the last category of scanners. Here, literally, we're saying that the scanner is mounted on an object that is moving, such as a robot or a drone, okay? And then it can now move around and scan the intended target. Now, don't confuse mobile laser scanners with mobile apps laser scanners. Our mobile phones today have so many mobile app scanners in them. And I've just put a screenshot on the left: Metascan, 3D laser scanners, okay, Metaport, Canvas, Sidescape, Modular, Scanivers, Polycam. Those are just some of the examples. There are so many of them today. You can actually use your phone to scan some of these apps to scan a building. And then one that we used in the past is Polycam, which is one of the leading 3D laser scanning application developed specifically for iOS. Now, that last point of Polycam allows you to export your scans in over a dozen file formats, including OBJ, GLB, MBX. Those are file formats. We're going to cover that concept later on. Now, the merits of 3D laser scanning. Remember, we started off by looking at the different types of surveying, okay? We spoke about the manual, the semi-automated, and the advanced automated techniques. And then we took 3D laser scanning as one of the advanced surveying techniques, okay? And then we've seen the different types of laser scanners, categorize them into mobile, wearable, mobile applications, and terrestrial. And now we want to see the merits of 3D laser scanning over conventional or traditional surveying techniques. Usually, laser scanning is very, very efficient. Okay. For example, if you use a laser scan to scan a building, you avoid so many journeys that you have to make to site. Okay. Imagine if I were to use the manual technique that I was doing, or that I did some years ago, to survey a building. I will go into that building using a pen and paper and maybe a tape, going around identifying defects, taking notes. I may go back to the office and realize that something is missing. I have to go back. So I may end up going to the site maybe about 10 times, or to the building about 10 times to have a complete picture. But with a 3D laser scanner, you minimize the number of journey times to site. Okay, and scans can actually capture up to 1 million points data per second. Okay, and you can use, very few people can be involved in scanning a building, and it's often very, very safe for a scanning team, because you can be located at one point and be able to scan the whole building instead of having to go around or climb the building from one using a ladder. Laser scanners, or laser scanning, is very, very accurate. That's one of the best advantages of 3D laser scanning, very, very accurate. And of course, it is very, very safe. It is a non-contact measurement system, okay, or surveying technique. It is a non-contact, non-destructive. You don't have to touch the object during surveying. And then the applications of 3D laser scanning. So we can use it in comparing the as-built model with the digital model, okay, or virtual model. So you see on the left there, that is what is on site. Then what we develop a digital replica, and that's what you have on the right. So you can always compare and see what are the changes. It can be used for project or progress monitoring. Okay? Imagine laser scanning a project that is evolving over time. You can always compare what you have on site with the digital equivalent or replica. And of course, you can use the scan model, okay, the point cloud data that you would have obtained from your scanning activity to generate a model that can be used for building retrofitting. The same, you can use your point cloud data obtained from laser scanning to generate a 3D model that can be used for maintenance and repairs of buildings. We can also scan historic buildings that have been there for ages, especially if it was designed with if it was designed long ago, and most of the time you don't have the drawings. And if the drawings even exist, they will hardly really match what is in reality or what the physical building is all about. So 3D laser scanner can be used, laser scanners can be used capturing historic buildings. And now, what is that process of scanning? You can see that, just put a slide there. It's a bit high level. We start from data collection using the scanner. Then we'll process the data, we organize the data. Then it's modeled now. Then the information is extracted from the model for different applications. Now, depending on the technologies, those are the different workflows there. I've just picked that from that site, Cancel. The link is below. You can actually go to a site and see the different laser scanning techniques that they've got, not in any way publicizing them. I don't know that company at all. So let me just focus on this one, which is by Faro Scanner. Of course, the activities to capture the as-built model. So we use a Faro Scanner to scan the building. And the next step is get the point cloud from the scanner that's scanning the building. You can now process this in the different software systems. Either use FaroSim, Edgewise, or even Revit. Now, depending on the file output from the Faro Scanner, it can directly be taken to Revit, and then based on that, the 3D model is generated, and that's what we're getting at the end there. The as-built Revit model. Yeah. So remember here, we mentioned something about software tools. For us to be able to move our point cloud from Faro to any of the software, if Faro's Sim or Edgewise or Revit, the two software need to be able to communicate, need to be able to talk to each other. So I'll have to define another concept here called syntactic interoperability. Syntactic or interoperability here in a nutshell refers to the ability of two software programs to be able to communicate and exchange data with each other. Okay, and I put some references there or citations. Okay, so in other words, we are saying that for two software to be interoperable or two systems to be interoperable, they should be able to read data or exchange data. Okay? One should be able to read data from another one. And in this case, Faro, the data from Faro should be able to be read by Revit, for example. And so we have a table there where we've actually developed this in one of our articles that we wrote some years back. That means if I were to buy a software like Trimble Reworks, okay, which is a software that we use in processing point cloud data, I'll need to first of all find out the type of files that it reads and the type of files that it generates. So that if I were to get my point cloud data into Trimble Reworks, I should know exactly what I'm going to take it to Revit or ArchiCAD and stuff like that. Okay, so we have the 3D laser scanners on the extreme left. Then they tell you the different type of software that can actually read data from those 3D laser scanners. So if you use Trimble TX, you are likely going to take the data into Trimble Reworks. Faro can go to Faro Sim. So, and then Leica Cyclone. And that is still another table just for your learning. And to simplify the workflow here, it's like we get a scanner like a Trimble TX8, we scan our building, then we process the data, then we can now export into different software. We export the data into different software, via Revit, SketchUp, or any CAD software. Now, the reason I've used Trimble TX in there is because we have it in our laboratory, our BIM laboratory. Now, that's just a simplified one that I need to show. It's exactly what I'm going to do in our part 2 of this presentation. So we're going to get our point cloud data from Autodesk Recap and then take into Revit, then use it in Revit to develop a BIM model. And then based on that BIM model, it can be used for different applications, what I would generally call NG modeling. These applications could be cost plans, could be project programming, could be rehabilitation, facilities management, documentation purposes, all the kind, even health and safety, all the kind of applications we think of in practice, we call that N, okay, ND modeling. But then our focus will just be on how to get point cloud data from Autodesk ReCap to Revit. And of course, it depends on the file format, the concept of interoperability. If we have our point cloud in ReCap, how does it get into Revit? We have to export it in the RCP